Hello dear friends, today's discussions is group theory, Galois group theory and also fixed field. We will summarizations, all of the summarization. So friends, first is definitions. Definitions. Let K be an extension of a field. K be an extension of a field, then the group of automorphism of K relative to F denoted by GKF. GK, F is the set of all automorphism of K, which leaves every element of F fixed. Which leaves every element of F fixed. So friends, this theory is our Galois theory. This theory is called Galois theory. So whatever we have learned, let K be an extension of a field F, then the group of the automorphism of K relative to F, and denoted GKF is the set of automorphism of a K. So friends, extension field, this is the F and this is our K, and this is the extension. This portion is extension field, and here F is fixed. Here F is fixed. So friend, F is fixed means here when we will map another portion, we will discuss very soon. Okay, then this is the F. This point is called F, and this is sigma. So sigma A be the point, A belongs to F, then sigma A equals to A. This is called fixed field. So friends, this is that I will discuss in the next portion. Number 2, let G be a subgroup of automorphism group of field F. Let F0 be the subset of F and consisting of those elements of F which are left fixed by every automorphism in G, and F0 equals to A belongs to F and sigma A equals to A for all sigma belongs to G. This is the main portion, that sigma such that F tends to F. This is the automorphism. Automorphism means K tends to K, sorry. This is the automorphism. This is the two set. This is F and this is K. This is the extension field and this is A, F, and this is K. So this mapping is called, this mapping is the automorphism. Automorphism means 1 1 on 2 mapping on 2. So friends, this is the main that what is fixed field. Fixed field, I hope I can clear this concept. What is fixed field and what is Galois theory. Galois theory I just revised because you can see more details in my Galois field theory example and lectures, but I just revise everything. Now next is let K be a finite extension of a field F, then K is said to be normal extension of F. K is said to be normal extension of F if the fixed field of G, K, F is F. K be the finite extension of a field F. let K be a finite extension of a field F, then K is said to be normal extension. So friends, normal extension when if the field of G K comma F, where F is fixed field is F, then it is normal extension. So friends, a normal extension is an algebraic field extension. A normal extension, must remember, is algebraic normal extension is algebraic field extension. Algebraic field extension L by K. L by K, for which every irreducible polynomial over K which has a root in L for which every irreducible polynomial over K which has a root in L and splits into linear factor in L and splits into linear factors in L. So friends, this is the algebraic normal extension. Example, Q root 2 is a normal extension of Q but Q cube root of 2 is not normal extension of Q. So friends, this is the counter example. So I give counter and counter example and examples and counter examples I give. And also it is the normal extension. K is said to be normal extension if the fixed field of G K comma F is F. Let K be a finite normal extension of a field F, then the group G K F means Galois K F of all F automorphism of K is called Galois group of K over F, and K is called Galois extension of F. Must remember friends, which you have to remember? You have to remember that let K be a finite normal extension of a field F. Then the group G K comma F, Galois group, this is the called Galois group G K comma F of all F automorphism of K. The set of all automorphism of K is called Galois group. Is called Galois group of K over F. K is called Galois extension of A. Number 5. Let K be a finite extension of a field F, then two elements alpha and beta of a field K are said to be conjugate over F if they have the same minimal polynomial over F. So friends, whatever we have learned, let K be a finite extension of a field F. Means this is the field, this is field F, and finite extension, this is the finite extension K, and then two elements alpha beta of a field K are said to be conjugate over F. Alpha and beta belongs to K if they have the same minimal polynomial over F. Then same minimal polynomial. So friends, minimal polynomial, what is the minimal polynomial, friends? I will discuss very soon. Let K be a separable normal extension of a finite degree over subfield K F. Then there exists 1-1 correspondence between the family of subfields of K. So friends, now we are discussing minimal polynomial. What is the minimal polynomial? Minimal polynomial of an element alpha of a field the polynomial of lowest degree having coefficient in the field. Means the polynomial of lowest degree having coefficient in the field, coefficient in the field such that alpha is root of the polynomial, alpha is the root of the polynomial. If the minimal polynomial of alpha exists, it is unique. So it is unique. The coefficient of the highest degree term in the polynomial is required to be 1. The coefficient of the highest degree is 1. Type for the remaining coefficient should be integer, rational numbers and real numbers or others. A minimal polynomial is defined relative to a field extension E by F. An element of the extension field E by F, the minimal polynomial of an element, if it exists, is member of Fx. The ring of polynomial in the variable x with coefficient in F. So I hope I can clear the concept. So what is the minimal polynomial? That if they have same minimal polynomial, they are the conjugate is said to be conjugate over F when the minimal polynomial are same. Okay, let K be the separable normal extension. Now we are discussing separable normal polynomial that are not inseparable are said to be separable. A separable extension is an extension that may be generated by separable elements. That is, elements whose minimal polynomials are separate. So I will write this again. What is the meaning of the separable extension field? Definitions. So separable extension, polynomials that are not inseparable. So first is inseparable extension. Polynomials which are not inseparable, which are not separable. This is the very best question. Which are not separable. Polynomial which are not separable are said to be inseparable. So a separable extension is an extension that may be generated by separable elements. That is, elements whose minimal polynomial polynomials are separable. So friends, in here the minimal polynomial must be irreducible. And alpha comma beta belongs to E are separable over F. Then alpha plus beta and alpha beta and 1 by alpha are separable over F. Alpha comma beta belongs to E if are separable over F, then alpha plus beta, alpha beta and 1 by alpha separable over F. So friends, I discuss what is separable field. So let K be the separable normal extension of finite degree over a subfield F. Then there exists one correspondence between the family of subfields of K. Then there exists one corresponding between this family of subfields of K and F and the family of the subgroups G, K, F. Further, E is any subfield of K such that E, subset of E and subset of K, then K, E is equal to order of J, G, K, E and E such that F means E such that F index of G, K, E in G, K, F, and E is the normal extension of F if and only if G, K, E is a normal subgroup of G, K, F. So friends, the condition is that this is F and this is E and this is K, and similarly another group is this is K, this is E and this is F. So this is the automorphism between this sigma. So that I will discuss. This is the fundamental Galois theorem. This is the fundamental Galois theorem I discuss. I have already proved this theory, fundamental Galois theory, state and proof fundamental Galois theory. I just discuss this portion for revisions. So what you see that K, E and order of G, K, E and E, F is equal to index of G, K, E in G, K, F. E is a normal extension of F if and only if G, K, E is normal subgroup of G, K, F. And E is a normal extension of F, then G, E if isomorphic to G, K, F and G, K, E, which is called fundamental theorem of Galois, fundamental Galois theorem. And a finite field is also called Galois. A finite field is also called Galois field. Important result on Galois theory. K is a normal extension of F if and only if K is splitting field of some polynomial over F, an element of K which remains invariant under each member of the Galois group G K, F of K over F is necessarily a member of F. An element of K which remains invariant under member of Galois group G K, F of K over F is necessarily a member of F. I hope I can clear that it is the member of element of K which is invariant under the each member of fixed field, means also the member of A, means if A is equal to A, this is the identity mapping, this is the invariant, this is called there is no changing. If it is not changing, so it should be also the member of F. Simple word, and means this is the K and this is F, this is F, and this is the member. A belongs to K and A belongs to F when it is invariant, means another automorphisms such that F and there is K and there is F, then F A is equal to A, then it is also belongs to F. Let K be a finite separable normal extension of field F of characteristic 0. Finite separable normal extension of a field F characteristic 0, then the fixed field of Galois group is F itself. Means you cannot get any others subfield of the fixed field. Where, because you subgroups you will not get. What is the characteristic 0? What is characteristic in algebra? The characteristic of a ring R, often denoted characteristic R, is defined to be the smallest number of times, and one must use the rings multiplicative identity 1 and sum to get the additive identity 0. If this sum never reaches the additive identity, the ring is said to be characteristic 0. Never reaches the additive identity, then that is characteristic 0. Characteristic are the smallest positive n such that 1 plus 1 plus 1 equals to 0. A field is called prime if it has no proper subfield. Example Q and Z by P, where P is prime and are prime fields. So friends, what is prime fields? Now our discussions point. Prime fields means a field is called prime. It has no proper subfield. Example Q and Z by P, where P is prime, are prime fields. The characteristics of a finite field. The characteristics of a finite field is necessarily non-zero, but the converse is not true. The characteristics of a finite field is necessarily non-zero, but converse is not true. The number of elements in finite field of characteristic P is of the form P to the power n, where n being some positive integer. The number of elements of finite field characteristic P is of the form P to the power n, the number of the elements. Suppose Suppose characteristic of the field is 5, then the number of elements of finite field may be 5 cube or 5 square, anything, but 5 is prime number. And each element of finite field has p to the power n elements, satisfies the equation x to the power p to the power n equals to x. If the finite field f has p to the power n elements, then f is the splitting field of the polynomial fx is equal to x to the power p to the power n minus x. And the multiplicative group of Galois field is finite field is cyclic. Now next topic is field. What is finite field? Finite field with finite number of elements is called finite field. Also, if order of an element of a field is finite, then field is called finite fields. Example, f is equal to zp5, this is called field where p is any prime subfield. If a subset f of a field f comma plus comma dot is called a subfield if f is itself field under addition and multiplications. Example, q plus comma dot and subfield is c plus comma dot, and r plus comma dot is subfield of c plus comma dot. This is the example of subfield. Now I will discuss what is prime field. Number 3, a field is prime field if it has no proper subfield. If it has no proper subfield, then it is prime field. The set f of residue classes modulo p, where p is prime number, is prime field if the characteristics of f is p. The set f of residue class is modulo p. P is prime number, a prime field if the characteristics of f is p. So friends, now the question is coming, what is residue class? So let's start to discuss the residue class. Let the definition of the residue class. Let m greater than 0. Let m greater than 0 be given for each integer a. We define residue a equals to x belongs to x congruent of a mod m. This is residue class. For example, m is equal to 3. If m is equal to 3 and a equals to 7, so residue of 7 equals to x such that x equivalent to 7 mod 3. equals to minus 5 minus 2 1 4 7 10 13 up to this value. So keeping m equals to 3, then we get 0 equals to x such that x equals to 0 mod 3 equals to, it can be written minus 9 minus 6 minus 3 0 3 6 9, this is 0, and 1 can be written residue classes of 1 equal to, it can be written x belongs to x equivalent to 1 mod 3 equals to minus 8 minus 5 minus 2 minus 1 minus 1 plus 1 4 7 10, this is, and equals to x such that x equivalent to 2 mod 3 that imply equals to minus 7 minus 4 minus 1 2 5 8 up to this is. So friends, this is the equivalence class of the 3. So I just give example because we are forgetting, sometimes people will forget what is the residue classes. So this is the residue classes. So the set F of residue classes modulo P, where P is prime number and prime field if the characteristics of F is P, and the field Q, an example Z by ZP. This is the another example, Z by ZP, and Q plus is prime field. The field Q plus is prime field as Q has no proper subfield. So I give some example that prime field example, that residue classes modulo P where P is prime number in prime field if the characteristic of F is P, and modular field with zero characteristic is called modular field. Zero characteristics is called modular field. Example, field of rational numbers is a modular field for characteristics is 0. Ordered field, a field is said to be ordered when it is ordered as an integral domain. A field is said to be ordered when it is ordered as an integral domain. Field extension. Now I am discussing field extension. Let F be a field and a field K is said to be extension of F if F is a subfield of K. or a field extension of a field f is ordered pair of k comma phi, where k is a field and phi is a monomorphism of f into k. So friends, now the question is coming, what is monomorphism? So friends, monomorphism is an injective homomorphism. Means injective means monomorphism is called injective homomorphism. Monomorphism is called injective homomorphism. Injective means one functions. Injective means one function. One is one to one. Suppose K is a field and F is a subfield of K. The injections mapping I such that F defined as Ix is equal to X. X belongs to F monomorphism. Hence K comma I is field extension of F. If field K is extension of field F, then K is vector space over F. If K is an extension of if K is an extension of F, then the degree of K over F is defined as the dimension of K as a vector space over F. Defined as the dimension of K is a vector space over F is denoted K such that F, thus the dimension of F K such that F is equal to dimension of K over F over F, and if K such that F is finite, that is K is finite dimensional vector space over F. And we say that K is finite extension of F. Important result. Let K be a finite extension of F. Let K be a finite extension of F, and L is a finite extension of K. Then L is a finite extension of F, such that F is L into L such that K into K such that F. If L is a finite extension of A, then L is also finite extension of F. Means this is this type of factor, friends. What is that? This is the F, and this is K, and this is L. So this is the conditions. And let L be a finite extension of F and K be a subfield of L which contains F. L be the finite extension of F and K be a subfield of L which contains F. Then K such that F defines L such that F. Important definitions. An extension K of a field F is called simple extension of F if K is equal to Fa. An extension K of a field F is called simple extension of F if K is equal to Fa, where A belongs to K. This is element A is known primitive element of K over F. This element A is called primitive element of K over F. Primitive element of a finite field is a generator of the multiplicative group of the field. A primitive element of finite field G F Q is a generator of the multiplicative group of the field. In other words, alpha belongs to GFQ is called primitive element if it is primitive Q minus 1 and its root of unity of GFQ. The minimal polynomial of a primitive element is a primitive polynomial. So friends, this question will come a lot of time. What is primitive polynomial? So primitive polynomial is the minimal polynomial of primitive polynomial. I hope I can clear this concept. Like q root 2 is simple extension. Example, q root 2 is a simple extension of the field q of all rational numbers. Example. Number 2. Fa is the smallest subset of K containing both F and A. Fa is read the subfield obtained by adjoining A to F. And let K be an extension of a field F. Let K be an extension of a field F. An element A belongs to K is said to be algebraic over F. An element A belongs to K is said to be algebraic over F if there exists a non-zero polynomial fx such that fa equals to 0. Otherwise, A is called transcendental element. Example number 1, root 2 belongs to Q root 2 is algebraic over Q since root 2 satisfies the polynomial fx belongs to fx and such that polynomial fx is equal to x square minus 2 belongs to qx and pi and e belongs to r are not algebraic over q. An extension K of a field F is called algebraic extension. Algebraic extension if every element of K is algebraic over F. An extension K of a field F is called algebraic extension if every element of K is algebraic over F. Example, R is not algebraic over Q. R is not algebraic over Q since pi and E algebraic over Q. the field C is complex number is an algebraic extension of the field R of real numbers. And number 5, that a non-zero polynomial fx belongs to capital Fx is said to be monic polynomial over if the coefficient of the highest power of x in fx is equals to 1. So I have cleared that what is minimal polynomial and what is monic polynomial. Number 6. Let K be an extension of a field F if an element A belongs to K is algebraic over F, then a monic polynomial of smallest degree over F, then a monic polynomial of smallest degree over F satisfied by A is called minimal polynomial over F, or polynomial of A over F. So friends, here is the another definition. Let K be the extension of a field F, and if an element A belongs to K algebraic over F, and then a monic polynomial of smallest degree over F over F satisfied by A is called the minimal polynomial of A over F. So what is the monic polynomial and what is the minimal polynomial? Monic polynomial means that the highest power of x in fx is equals to 0, equals to 1, and minimal polynomial is the monic polynomial of smallest degree where f satisfied by A. A is algebraic over F. Then monic polynomial of a smallest degree of over F satisfied by A is called minimal polynomial. So this is the minimal polynomial and monic polynomial. The degree of minimal polynomial of A is n, and A belongs to K is said to be algebraic over F. If the degree of minimal polynomial of A is n, then A belongs to K is said to be algebraic over F of degree n. Important theorem of field extension. Theorem 1. Every finite extension of a field F is an algebraic extension. Every finite extension of a field of F is algebraic extension, but the converse is not true. Every finite extension of a field F is algebraic extension. And let K be an extension of F let K be an extension of F, and let A belongs to K be algebraic over F, then there exists a unique monic irreducible polynomial fx belongs to fx of least positive degree such that fa equals to 0. Number 2, if gx belongs to fx is such that ga equals to 0, then fx divides gx. And theorem 3, let A belongs to K be an algebraic over F, and let fx be minimal polynomial over F, then fx irreducible over F are equal. A belongs to K be an algebraic over F, let fx be minimal polynomial over F, then fx is irreducible over F are equal. Let A belongs to K be algebraic over F, then any two minimal monic polynomials over F are equal. Theorem 5. Let K be an extension of a field F, and A belongs to K be algebraic over F, then fa equals to fa, and where fa is equal to this. And theorem 6, let K be an extension of a field F and element A belongs to K if and only if A such that F degree of F such that F is finite. This degree means extension field degree is finite. Note, degree of the unique monic polynomial over F. This notation fa such that F equals to degree of the unique monic irreducible polynomial over F satisfies by A. And theorem 7, if alpha comma beta bk belongs to K are algebraic over F, then alpha plus minus beta, alpha beta and alpha by beta are all algebraic over F. In other words, the elements in K which are algebraic over F from a subfield of K. Theorem 8, let F be a finite field and K be a subfield of A, then let F be a finite field and K be subfield of F, then F by K is algebraic. Theorem 9, if A belongs to K is algebraic over F and odd degrees, then F is equal to F square. Theorem 10, let K be an extension of a field F and Fx belongs to Fx, and there exists Gx belongs to Kx such that Fx is equal to x minus a, Gx plus Fa, and degree of Gx is equal to degree of Fx minus 1. If Fa is equal to 0 and a belongs to K is a root of Fx, and Fx x minus a divides Fx in Kx, that implies Fx is equal to x minus a Gx. Theorem 11, polynomial of degree n greater than equals to 1 over a field can have at most nth roots in any extension field of F. Theorem 12, let Fx be any polynomial of positive degree in Fx, then there exists an extension K of F in which Fx has a root in K of F, in which Fx has root in K and K degree of K such that F K field extension over F degrees less than equals to degree of Fx. So Fx has root in K. So let Fx be any polynomial of positive degree in capital Fx. Then there exists an extension K of F in which Fx has a root in K of F, in which Fx has root in K. If Fx is irreducible polynomial, then equality holds. Means let Fx belongs to capital Fx be a polynomial of positive degree n over a field F, then there exists a finite extension K. Let Fx belongs to capital Fx be a polynomial of positive degree n over a field F, and then there exists a finite extension of K of F of degree at most n factorial. Degree at most n factorial, that is degree of K field extension K over F less than equals to n factorial. Fx has at most n root in K. Now friends, we are discussing about cyclotomic polynomial. What is cyclotomic polynomial? X to the power n minus 1 is equal to, this is the sum of product of x to the power d minus 1 into mu n divided by d. Fundamental property of phi nx. Phi nx is irreducible over Q, n is prime and x belongs to x plus 1 Eisenstein, and n prime power x plus 1 is Eisenstein criterion, and Frobenius automorphism. Frobenius automorphism is let F be a field of characteristic P, then the Frobenius automorphism on F is the map of phi such that F tends to F, which map alpha tends to alpha to the power P for each element alpha of F. This is Frobenius automorphism. Now friends, I have already discussed what is the characteristics of ring. So friends, let's try to solve some proof. Let if A is any algebraic number, prove that there exists a positive integer n such that Na is an algebraic integer. So since A is an algebraic number, there exists a non-zero polynomial fx belongs to qx such that fa equals to 0. Let fx equals to x to the power r plus alpha 1 x to the power r minus 1 plus alpha 2 x to the power r minus 2 plus dot plus alpha r, and alpha I belongs to q. We can write alpha I equals to mi divided by ni, where mi comma ni both are integer, belongs to integer, and ni greater than 0. Let n equals to n1 n2 n r, which is a positive integer. From equation 1, this is the equation 1. From equation 1, we get n a to the power r plus m1 n2 dot nr a r to the power r minus 1 plus m2 n1 n3 dot ni n to the power r minus 2 a to the power r minus 2 plus plus mi n1 n2 n r minus 1 n to the power r minus 1 per r. So friends, we can write this way that x to the power r plus m1 n2 nr x to the power r minus 1 plus up to plus mr n1 n2 dot n r minus 1 n to the power r minus 1. This is the monic polynomial. You see, na satisfies integer monic polynomial. Hence, na is an algebraic integer where n equals to n1 n2 nr is a positive integer. N equals to n1 n2 nr. Number 2, let alpha comma beta belongs to k be algebraic over f of degree m and n respectively, and let m and n be relatively prime, show that f alpha comma beta is a degree mn over f. Since we have f alpha such that f equals to m and f beta such that f equals to n, then we show that f alpha such that f equals to mn, and then we show that k is equal to mn. Now if alpha comma beta such that f equals to f alpha comma beta such that f beta and f beta such that f and k equals to f alpha comma beta such that f beta into n, and that implies n divided by k, but m and n are relative prime, so that m by k, so that m divisible by k means k is divisible by n, and n is also k is also divisible by n, so k is divisible by n, so m and n relative prime, and m divisible by k, k is divisible by m and k is divisible by n, then again we have f alpha comma beta such that f less than equals to f alpha such that f and f beta such that f. So k less than equals to mn. So this is the equation number 1, and this is equation number 2, and this is equation number 1. So both from 1 and 2 we have k equals to mn. So it is proved. The theorem is proved. Next, this is my last theory. Show that an element alpha belongs to K, alpha belongs to K, and the finite extension of a field F generates the whole extension if K such that F and alpha such that F is degree of alpha over F. We know that F alpha such that F equals to degree of alpha over F equals to, suppose alpha generates the whole extension, then we have K is equal to F alpha. Therefore, K such that alpha F equals to F alpha such that F is equal to alpha such that F, using equation 1. After that, conversely suppose K such that F is equal to alpha such that F, then we shall prove that alpha generates. We shall prove that alpha generates the whole extension K. The whole extension K. That is K is equal to F alpha. By transitivity extensions, we have K such that F equals to K such that F alpha into F alpha such that F, and K such that F equals to K such that F alpha equals to alpha such that F, and this equals to K such that F alpha into K such that F. This is the main formula. Suppose K alpha is equal to alpha comma F. This is the I have already told. So what we get, 1 equals to K such that F alpha, and that implies K equals to F alpha. So hence the result, proof. I hope I can clear the concept. Thanks for watching.